All right. Hello, everyone. Welcome back to Comp 2160 Programming Practices. I hope that you are all doing okay today. I was thinking about stuff that you could do on the weekend when you don't have an assignment due. I'm assuming that you don't have any more assignments due after Friday. What other assignments do you have that are due? So just ignore 2080 and drive north of the city for several hours. Yeah. And there's a place called Narcissus. Has anyone been to Narcissus before? A couple people? Narcissus is this really cool place. It's called Narcisse, Manitoba. And it's a provincial park. And the I'm not sure if anyone really dislikes snakes, now's the time to stop listening and paying attention to whatever I'm talking about. I'm not sure if this image is actually bigger. No, it's still really tiny. The Narcissus is a place where there are snake dens in Manitoba. And it's, like I said, it's about an hour and a half north of Winnipeg, and now is like the time to go. And basically what happens at the Narcissus snake dens is that these are garter snakes, so they are small and they are harmless. They don't bite, they eat bugs. Like they're not going to come and bother a person. But in the snake dens, the snakes are basically coming out to mate. They're coming out of hibernation and they are coming out to mate. And in the pits, like there's holes in the ground that you can go look in, and there's just snakes everywhere. And they are kind of like also crawling around on the ground to go towards the snake dens. And my favorite memory of Narcisse is going there and walking around, and there was a little girl there with her family. And the little girl is running up to her mother with two snakes in each hand, kind of like, look. And the snake, they are harmless. You can pick them up, and like once you are holding them, they're docile. They're not going to bite you. They're nervous because you're a giant thing holding them, but you can pick them up and they're not going to bite you. And now is the time of year to go to Narcisse. So if you do have some time in between proving whatever you're proving in 2080 right now, this is worth going to check out. It only kind of happens around this time of year, so like in the last couple weeks of May is the time to go and see these snake pits. This is a really unrelatable anecdote, but I took my kids there too. I've taken them there a few times, and this has resulted in us owning a snake for a pet at home. It's a corn snake, so it's also quite small and harmless. Like it doesn't, it's not going to bite us if we pick it up. But yeah, my son has a snake for a pet now, which is not something I ever anticipated having as a pet in my house. But that's extremely unrelatable, so I'm sorry for that. But yeah, I really like going to Narcissus, so it's worth checking out if you're new to Manitoba, or even if you've been living in Manitoba your whole life. We're going to be working again on strings.c from yesterday's lecture. At the very end of class yesterday, we changed the signature of the string copy function, but just the signature of the forward declaration of the function. That's as far as we got. The code that I posted on the course webpage has that change, but the comments that I wrote in the README are true, which is the code doesn't compile as it is because we haven't gone to the function definition to change that same part of it. And we haven't actually finished what we're doing, but I wanted to put that example up. We're going to look at this pretty soon today, and what I want to do with this is I'm going I'm going to start by deleting a bunch of stuff so that we just have string copy so that we can focus on that, because the other parts of the code are not as relevant for the example that we're looking at today. By the end of today's lecture, what I am hoping for you to be able to do is write safe code in a programming language that makes it difficult to write safe code, and describe concepts of in-application memory management such as the runtime stack and the heap. Today, these two learning outcomes are directly related to each other. Really specifically, this part, the runtime stack, and writing safe code in a programming language that makes it easy to write unsafe code. To do these two things together today, we're looking at beginning to use pointers in a program safely. The example that we're going to look at is using pointers in a program unsafely. But I want you to look at this as a counterexample as opposed to a way that you should do it. I want you to continue to be able to do this. We started doing this kind of in theory last time, where I was like stepping through some code and showing you this is what happens when you call fgetS. This is how it's pointing back to the stack allocated array in the main function. But I want to do this in the context of the functions that we are completely in control of and can see this time. And we're going to look at another function called scanf in C. If when you were starting to work on the assignment, you were looking at how do I get input in my program in a way that's not getchar, you might have seen scanf. Someone at the back yesterday asked, is it okay to use scanf? This is a variant of the scanf function. I want to look today at why it's not safe to use these functions, so the results of this. And I have an example of some code that we'll look at that will justify why it's not safe to use this with a fairly good example. I want you now, so after these things, it's kind of a little bit of a grab bag of stuff that we had leftovers. I want you to be able to write code that takes advantage of its environment through redirecting of standard input and output for file I/O. I really just want to formalize the idea of input and output streams and redirection. I don't want to spend a huge amount of time on this. The one part that I want to spend and dwell a little bit on is something called a pipe, which we haven't talked about. We did talk about redirecting input. We've talked a little bit about redirecting output, but I want to dwell on sending data between programs with this thing called a pipe. And I want you to be able to explain what standard input and output are, giving examples of each. And I want you to be able to choose and use redirection operators and pipes. So given some context, I want you to be able to make that choice. The final thing is I want you to be able to build and execute programs from a command line environment. In this case, for this learning outcome, I'm really specifically meaning, let's talk about the different phases that a C compiler goes through. So I want us to actually be able to see what happens with preprocessor directives. We've been blindly writing now number sign include and number sign define, but I want you to see how the C compiler is transforming your source code with those preprocessor directives. I want you to be able to see how the C compiler is transforming your code into assembly language. I want you to see how the C compiler is translating assembly language output to binary, and I want you to be able to see, once we get to this binary, how is it actually taking all the functions and stitching everything together at an extremely high level. I'm not going to be getting into the details of like the compiler is opening your binary file here and it's doing this to it and this to it and this to it. It's more like these are the phases of compilation. This is approximately hand wavy. This is what's happening. You can see some of these things in later courses when you get to them, like operating systems specifically. If you haven't figured out that I like the operating systems course yet, because I keep talking about the operating systems course, I like the operating systems course. And I got to stop talking about operating systems. Okay, so this is kind of where we ended last time. We got to this point of being able to think about communicating addresses between things. Let's all chant this together. An array is not a variable. An array is an address. Thank you. An array is not a variable. An array is an address. A pointer is a variable whose value can be an address. So pointers here are giving us the ability to communicate addresses around in our program. The declaration of pointer type is very similar to the way that you're declaring other primitive types, except you're putting this asterisk in. Without the asterisk, int val says I have an integer. Without the asterisk, char val says I have a single character. Without the asterisk, float val says I have a single float. With the asterisk, what this is saying is, if you follow the address that's contained in this variable, you will find an integer. If you follow the address that's contained in that variable, you will find a character. If you follow the address that's in this variable, you will find a float. This is a way for us to communicate addresses around in our program. When we started with arrays in C, we were able to see immediately that we could not return an array from a function, but we could send data back from a function, complex data, by having these output arguments. So you accept two arrays. One of them is the place where you're writing to. The other one is where you're reading from. But when we tried to change it to return an array, our compiler just immediately said, nah, you can't do that, sorry. If we are going to use these ideas of pointers, I want to be able to communicate addresses to different parts of my program, then I can return this. I can return an address. I can return a variable that contains an address, and we can start to work with that. So I'm going to pop over to my terminal here. At the back, is this big enough for you to see? Is that okay? A little bit bigger? Good, thank you. So I've got lecture 6 here. I'm going to make a directory, lecture 7, and I'm going to copy lecture 6 strings.c into lecture 7. I'm going to edit strings.c. And as I said, I actually want to start this by deleting a bunch of stuff because I really just want to focus on the string copy part. And I don't want all these other things that we've got to get in the way of that. So I'm going to start by deleting the forward declarations for length and compare. In Vim, we can enter something called visual mode to do like highlighting multiple lines by pressing V on our keyboard. You'll see at the bottom there that it's changed to visual mode instead of insert mode. And when I'm in visual mode, I can start using my arrow keys to highlight multiple lines. And once all those things are highlighted, then I can use the same kind of shortcuts to do things like deleting things. So I'm going to hit D on my keyboard, and it will just delete all of those lines for me. If you want to yank or copy a bunch of lines, it's the same thing. You can do V and then highlight a bunch of lines with your arrows, and then Y, and it will copy all of those lines inside of Vim itself. It's not putting it in your Windows clipboard, but it's going to let you do that. So I'm going to scroll down here. I'm also going to go through and delete the references in my main function to those other functions, so I don't have length anymore. I'm actually just going to delete everything that's in the main function after a new name. So this is what my main function looks like right now. And then I'm going to delete all the function definitions down here for string length and string compare. So here we are at the top. We've got our main function that has a couple of arrays being declared. We've got the forward declaration for string copy. We've changed the signature for this function. So we're returning a pointer to character right now. If you follow the thing that string copy returns, what this is saying is if you follow the thing that string copy returns, you will find a character. Character pointers, you'll find a character. An array is an address, and the address has the first character in a string. If we follow this pointer to this memory location, that's the first character. It might just be a character, but it could be more characters that are then followed by a null terminator. Pointer and array are kind of synonyms for each other in C, kind of. An array is just an address. A pointer is a variable, but you can almost use them interchangeably. And in fact, one thing that we didn't know was that this array reference here, when this gets compiled down, it's in the background, it's actually just transformed to a pointer anyway. We can use these square brackets with pointer types, and it will add numbers to the things that we're looking at. But let's leave this the way that it is right now. I want to come down to my string copy function, the actual definition of it, and I want to change the signature of this to match the forward declaration. So I need to have this be a pointer type, character pointer type that I want to return. This only has the source and the number of characters that I want to copy. Now that I've got my function string copy returning something, I've got to have a return statement. I have to actually return something. Before, because I was using that output parameter or that output argument, I could just write into it and then end the function, and then whatever the caller has asked me to do will just be there for them. I don't have to return anything, but now I have to return something. So I need to declare an array in my function. I'm going to call it target because conveniently that's what I called it as an argument to my function. In C, when I declare a stack allocated array, I have to give it a size. I must give it a size. Best practice, I want to do preprocessor directive, define target length. What should I pick here? What's the maximum size value? New name size. Okay, I'll be consistent here. New name size 50. Okay. I could, yes. I could actually just put new name size. So the question is, can I not put new name size here? I can, yes. But kind of like I'm declaring this constant up here because it's related to this specific array. I want to do something similar. String copy is a function that's independent of name or new name or whatever. So I want to have it have its own constant. No. And I will show you why in a little bit, closer to the end of class today. You could put new name size there. I'm going to put 50, and I'm going to put target length here. So we've got this array, best practice. I'm going to initialize it to 0. I'll come to you in just a second. I want it to be filled with null bytes. Yeah. That's a good question. So the question is, why can't I do char target, and I'm going to do it this way, strlen source. That's ultimately your question, right? Yeah. You can do that. The C compiler will let you do that, but it doesn't mean what you think it means. It's a subtle difference. This is an array that has a fixed size. When the compiler emits code for this function, it's also emitting code for, like, how do I change the stack? Our compiler is kind of doing that in the background for us. We don't really care or know how a stack frame gets added to the stack. Our compiler does all that work for us. The compiler, as it's going through and reading your source code, is looking and saying, okay, there's an array here. It's got this many bytes. This is how much space I need to reserve for this. Here's an integer. I need to have space for this. Here's an integer I have, I guess there's no integer here, but here's an integer. I need to have space for that. So as it's compiling your code, it's able to pre-compute how big the stack frame should be. With this, It cannot pre-compute how big the stack space should be, because every time you call this function, this value could change. So there's no way for it to know how big this is. Modern C compilers allow this, and the way that they work is that they will allocate those strings in a slightly different place than the runtime stack. And that's going to lead to potentially unexpected behavior. Another problem here is that if this length of string is like absurdly big, let's say we have a megabyte size string, it's going to cause that code to crash where it wouldn't have crashed otherwise. What we're doing, to be clear, at 1,000,000%, even the way that we're doing it right now is the wrong way to do it, and we shouldn't do it anyway. But doing strlen here is just subtly different than having a fixed size array, to a point that I would suggest that you try to avoid doing that. Ah, okay. Thank you for clarifying, and I'm sorry for just going off on you. The answer is the same, though. The answer is the same. So if I say characters here, that's what you meant? Yeah. If you do it like this, the answer is the same. Each time I call this function, it might be with a different number of characters. And so I can't pre-know how big that array is going to be. The compiler can't know. Does it fail? Yes, it does fail, but there's no array index out of bounds exception. So you're on the right track here. This is what I'm going to say. This is how I'm going to answer your question right now. You are on the right track thinking about this stuff. You are 100% on the right track thinking about this stuff. I'm not going to leave it like this for the reasons that I explained. And I'm going to leave this for you for a slide that I have later about why things in C might be unsafe. And it's related to, I'm a terrible programmer. That's what it's ultimately related to. Okay? Yeah?
If you left the characters variable in there, the compiler would actually throw a warning where it says it's not initialized, or maybe this character is initialized.
Okay.
That's why I know this one.
Okay. Strlen will work. I've seen it work before, but like I said, it's not doing what you're expecting it to do. You had your hand raised. Okay. Okay, so I realize that's kind of a non-answer to your question, but I hope that you're okay with what I've said. Okay. So we've got this array. We've initialized it to 0. Now that we've got a return type, we must return this. So I'm going to say return target. Again, array and character pointer are functionally equivalent in a lot of places. An array is an address. A pointer is a variable that can have an address as its value. When I return target, it's kind of the same as having an int return type on a function and returning an integer literal. We don't have a variable that has that literal. That value is what's sent back to the place where this function is called. So even though the type target is character array, stack allocated character array, we can return it as a pointer because it's an address. This is kind of a literal address that we're returning back to the caller. I would like now to call this function. I'm going to call this by saying, first of all, add a new pointer type. I'm going to change this one. I'm going to delete line 20 here. I'm going to change its type to pointer. And I'm going to delete all this other stuff behind it. So now we have a pointer that's equal to new name. And what I'm going to say is it's equal to string copy. The thing that I want to copy is my name. And I want to copy 8 characters, excuse me. I want to copy 8 characters. I'm going to check to see that this worked. So printf, original name, %s, new name, %s, \n, name, new name, semicolon. I'm going to pop open another terminal to my side here. Got strings.c here. I'm going to compile it. We got two warnings. One is unused variable. That's simple enough to fix. We'll delete Walter here. Poor Walter. Try to compile it again. We've got a warning. Address of stack memory associated with local variable target returned. I'm going to list the contents of this directory. I got a program out. I did get a program out. I'm going to run it. Strings. It seems to have worked. It seems to have functionally worked. I've got a copy of that string. I want to know, have I actually printed out two different things? And so I'm going to actually ask for the address of each of these items. I'm going to do copy this and paste it. And I'm going to change this to %p. %p is a pointer type. This is going to print out the address of those things. What I'm really looking for is I want to confirm that these are both located in different places in memory. I want to see that this is actually a copy of the thing that I had originally passed into it. So I'm going to compile it again. I'm going to run it again. And just forgive me for a second. I'm going to expand this. And while these addresses do start with the same prefix, 0x7FFFF872E1D, the end part of these addresses is definitely different. They are not the same variable. They're not the same value. There's two different string arrays that have the same contents right now. I'm going to come back to this code, but I want to go back to my slides for 1 second. When I wrote these slides, I called it copy instead of target, but it's the same error or the same warning message. Let's just ignore the warning for now. Let's just ignore the warning. Don't ignore warnings. Don't ignore warnings, but let's, for the sake of this class right now, let's just ignore the warning. Here's that same code. I'm gonna bring Walter back. I'm gonna bring him back. And I'm going to have another new name. I'm going to say string copy. Walter has 6 characters in it, so I want to copy 6 characters. And I'm going to copy these 2 lines. So I'm doing a yank Y and down. Y says copy, down says copy this line and the next line. And I'm going to paste those. I'm going to amend to this, new name and cat name. I'll hold this up here for just a second. Okay. I'm going to zoom out, so I'll just collapse this a little bit. I'm going to compile this code again. I'm going to make sure I've written this, and then I'm going to compile it. And I'm going to run it. I'm going to expand the output here for now. I'll bring the code back in just a second. Do we see something weird about what's happened here? Do we see something weird about what's happening here? They are the same. They're the same array. They're the same address. And I've overwritten what was in another variable, another thing that had something unique in it. I've just completely written over that. I'm going to do one more thing here. That's probably enough. I'm going to write this out. I'm going to compile my code. It wasn't enough. It's not doing what I want. Clearly, it's not doing what I want. I'm trying to overwrite a whole bunch of stuff. Go for a nice round 1500 here. Let's see. It's still not doing what I want. That's not 1500 ends, though. That can't possibly be 1500 ends. How can I tell? Okay, so 1, 2. I suppose the right way would be to use strlen to count how many ends there are. So in Vim, there's this cool thing called insert mode, or visual mode, where you can highlight a bunch of stuff. And then you can do Y to yank it, and then you can do P to paste it. Syntax highlighting has stopped now. The code, like, surprisingly still compiles. Oh, I remember. I see what the problem is. We're only copying so many characters of this thing. That's the problem that we've got. So I'm going to change this to say strlen name. I want to copy everything. My problem was that I had made it too resilient to this kind of a fault. You can use strlen by including string.h. That is what I wanted to see. That's what I wanted to see. Fish, the friendly interactive shell prints out a little bit nicer of an error message than some other shells do. Other shells will just print out the words segmentation fault. I'm sweating up here because I'm like, oh no, it's not working the way that I hoped it would work. Don't ignore warnings. Don't ignore warnings. This is a cautionary tale. Let's see what's happening here. Remember from last time, when we call a function, a new frame is added to the stack. And that frame is added to the stack with enough memory for all variables that are declared inside the function that's being called. The machine is going to start executing code inside of that function. When we return, the frame is popped off of the stack. And whatever happens to values inside those stack frame kind of depends on the platform. The behavior on my machine is going to be different than what you see on Windows, is going to be different than what you see on Mac OS. It might be all the same, but for each of those operating systems, it can be different. I want to quickly draw a picture of what's happening here. I'm not going to go quite as detailed as the code that we were looking at last time. On line 21 here, we are in the main function. So here's our stack. And right now, our stack has main in it. Inside of main are the stack allocated arrays for name and cat. Those are both inside here. There's also enough space for a pointer that's called new name and a pointer that's called cat name. On line 21, when we call string copy, this new frame is added to the stack. This one is going to be for string copy. In string copy, the stack frame is going to have enough size for this target array. So I'm going to draw this out as a little bit more of a traditional array that we've seen, and I'm not going to draw all 50 characters here. But we're going to have this target, and it's going to have space for characters inside of it, and then dot, dot, dot. As we go through that loop, we're populating it. So as we're populating it, the very first time that we called it by passing 8, it's kind of doing what we want, but it's doing it to the array that happens to be inside of this function. So it's going to start actually doing FRANKLIN. It's going to do that. When we return from this function, this stack frame is going to be removed. But what we're returning to our main function is the address of this array. That's what we're returning, is the address of the array, and that's going to get popped off when we do the return. When we call cat name is equal to string copy, a new stack frame is going to be added. And it's going to start overwriting. I'm going to zoom in a little bit here. It's going to start overwriting what's in there right now. So it's going to start writing WALTER \0. This is that first behavior that we saw. This new name is pointing at that array that we've got there. And when we return again from this stack, we're returning this pointer into cat name. That's why we got that name changing behavior. The segmentation fault is happening here when we change this to Sterlen. Name, I want to copy like 1,000 characters. What's happening here, I'm going to copy this. What's happening here with copying 1,000 characters, or thousands of characters, is that it's copying F R A N K L I N N N N N N N N N N N N and literally this, it's copying it over top of the stack frame for main. There is no array index out of bounds exception in C. Once we start writing past the end of the array, it's just going to clobber whatever happens to be next in memory. The things that are next in memory after the array that we have declared on the stack for this function are things like the stack frame for the previous call that we were in, return addresses, the stuff that the stack is using to keep track of where we are and where to go back in the code that we're working with. The warning that my compiler emitted was, hey, you're returning this local stack allocated array. Maybe you shouldn't do that, but I'm sure you know what you're doing, so here you go. Here's your program. And the result of that is code that's going to start overwriting its own state in a way that we're not expecting it to. Any questions about this? Yeah, so that's part of it. You should have some hard limit. A good practice here would be to say, I'm passing Sterlen into this function. A much better practice, rather than just blindly copying up to characters, is to say if characters is less than target length. This would fix that one problem. If I add a conditional statement, C is not giving us array index out of bounds exceptions, but it is going to let me at least forbid you from doing it in the first place. This fixes one problem. This fixes one problem of clobbering those stack frames if you've got a string that's too long. This doesn't fix this problem of the same address being in both of these variables, referring to exactly the same location in memory. That's a good point. Thank you for raising that. Very generally, I'll get to you in just a second, when you're working with arrays, best practice is define their length as a constant, initialize them to a known value, and if you are accepting as input an argument that you are going to use to operate on an array that you have declared, use a conditional statement to verify that the value actually is within the bounds that you're expecting it to be.
One, how did you shift the index to multiple lines at once?
Oh, in Vim. So there's an auto indent flag that you can turn on in Vim. Okay. Sorry, I wasn't 100% sure what you're talking about. Okay, so this is where I'm stopping verbalizing what I'm doing in Vim and just getting on with it. So this is visual mode again. So the question is, how did I move multiple lines over? If I highlight them with visual mode, so enter visual mode with V, use the down arrow, and then if I do greater than symbol, it moves it that way. If I highlight them all again and I do less than symbol, it moves them back.
And then back to the actual.
Yes.
String copy, and then within the string copy parameters, you add another function.
Yeah.
On the stack, would that create a whole new frame because it's another function, or would it say within?
That's a good question. So here, this is your question, is about, I've got this other function that's in here. So technically what's going to happen here on line 21 is that we're going to do strlen first. That stack frame will be added and then removed, and then what the value here will be replaced with whatever strlen returns, and then a stack frame for string copy would be added to the stack. So they're discrete operations. They're not going to be like nested inside of each other. Yeah. Yeah. If there's a function inside string copy, then yes, that would be added to the top of that stack frame. Yeah. Yeah.
In the context of the assignment, would an assert statement be good enough in place of the if statement that you have, or that the size is less than 50?
We are going to talk about this later. So the question is basically, what about putting this here? Characters is less than target length. We're going to talk about this later. This is a feature that's called design by contract. It's more about stopping you at development time from giving invalid values to functions, but you can turn this off. Assertions can be disabled in code, and if you want to prevent this from still happening anyway, an assertion is going to give you an error and it will stop executing. A conditional statement will just not do anything. But we'll talk about it more later. Yeah. Any other questions? Okay, awesome. Okay, so I will post this copy of string copy up. This one will not segfault. If you want segfaults, I'm going to delete the assertion. If you want segfault, delete this. Delete the conditional. And I'll try to make sure that I include that in the README that I put alongside this. But this one will still fail in terms of like overwriting variables that we're not expecting to be overwritten. So I'm going to pop over here to my slides. The related point here is why is scanf bad? Scanf is a function that you can use for input. I want to start by looking at the manual page for this pretty quickly. And then I want to read and run an example code. So I'm going to say man3 scanf. Scanf is a function that does input format conversion. And what it does is it takes as input a format string. The format string for scanf looks a lot like the format strings for printf. So when I do %s with printf to print out a string, scanf will let me say %s, and it will read a string in for me. If I want to get numbers, I can say %d, and it will read a number in for me in the same way that printf will print out a number. Scanf works by passing input arguments to it or output arguments to it, and it will write into them. So with fgetS, we passed a buffer. For scanf, if you wanted to read a string, you would also pass a buffer to that. I'm going to quit this manual page, and I'm going to copy something here from my course directory. Summer 2, lecture 7. I'm going to copy this code here, and I'm going to open this. Please heed this warning. Please heed this warning. This is not my original work. This is from an article by Nguyen Tien Su. And if you want to read more about this, you can follow this link. I'm going to give you just a couple of seconds to read this code. It's not very complicated. Give me a thumbs up when you're ready to go. Okay. I'm just going to compile this code and run it. There are no warnings emitted by this code. As far as our C compiler is concerned, this code is great. I'm going to run secure, enter my password. We are currently blocked. So remember I used that keyword last time. We are currently blocked on this line. Execution has halted. It's waiting for us to type something in. Scanf and fgetS, when we pass std in, will block waiting for input when I haven't typed anything on my keyboard yet. If I enter the wrong password, I should make sure that it adheres to password security principles. So it's got to have an uppercase character, and it's got to have a digit. No, 1 is better. That seems to work. We're comparing it to the secret, Hunter2 here. We get wrong passwords. We do not set success. We exit because it's the wrong password. If I run secure again and I type in the correct password, it works. So fine, it works as expected. If I run this one more time, wrong password, access granted, and then segmentation fault. Success, by default, is 0. Scanf, like the function that we just wrote, string copy, accepts as input. Well, at least in this case, it returns something, but it doesn't really check to see anything about how long it should be copying. Scanf is taking passwords, and it's reading a string until a delimiter is found, which in this case is the enter key on my keyboard. This array has 15 slots in it. I've typed in many more than 15 characters here. Scanf is blindly writing to the array. I'm going to pop my tablet open here again. Scanf is blindly writing to this array. The array right now, the way that this function is looking, in terms of our stack, is that it has 15 elements, ... At the bottom. This is password. In our stack frame, immediately below password, even though the order is kind of inverted here, is success. These are just locations in memory, and they happen to be immediately beside each other. So when I type in password 1111111111111, scanf is going through and diligently saying, cool, I've got a buffer that I can write into, PASSWRD111111, even though this was 0 before. It's being overwritten with a 1. a 1. It's being overwritten with a 1. And so our conditional statement here for string comparison does indeed fail the way that it's expected to, because password does not equal hunter2. But because success was overwritten by scanf here, if success does actually work, that condition passes. Scanf is bad in the same way that string copy was bad, when we didn't have that conditional statement to check to see, can I actually write or should I stop writing before I get to this point? fgetS solves this problem by having you pass in an argument that says, this is how big the buffer is, and you should stop writing when you get to this point. I'm going to put this code up along with the other one. If you want to read a little bit more about what's going on here, you can read that article. This is a buffer overflow exploit. If you've heard those words before, this is what a buffer overflow exploit is it's writing past the end of the buffer, changing other values and variables, and then able to get to other places where you're not supposed to be able to get.
Is it also just hold the stack overflow?
The stack overflow is literally when you run out of stack space. Yeah. And I mean, that can be exploitable. I'm not really into that scene, so I don't really know, but this is a buffer overflow exploit. Okay. Any other questions? We are good. Yeah. Okay, so that's a really good question. The answer is no, not with what we see right now. The answer is in operating systems. When I drew that picture of this is what our memory looks like, we've got code, heap, and stack at the bottom. That is also an illusion that will be revealed to you when you get to operating systems. Operating system memory is also specially isolated from code. In conjunction with the hardware is able to protect certain access to different parts of memory, but your code doesn't even know that the operating system exists. As far as your code is concerned, it just has that address space and it's able to work in that. Okay, awesome. I'm putting this back up here, and I'm going to ask you to just pass this around right now. If you don't have a pen, I do have a pen. I'm looking for you to write anything right now. It can be a single word. It can be a full sentence. It can be whatever you want. Don't write your name on this paper. Turn it in to me at the end of the class. This is obviously not for marks. Feel free to talk to your neighbor about what you think the answer to this question might be. Absolutely. Got lots of pens and pencils up here. If you need to borrow one, stick your hand up.
I don't think we got it.
Oh, I'm sorry. I'm going to give you 2 minutes to do this. Talk to somebody. If you feel comfortable talking to other people, think inside your head if you don't want to talk to other people. Yeah. Would you mind throwing that one away from me?
Yeah, sure.
When you're done? Thanks. Okay. If you've written something down, great. If you haven't finished writing something down, don't worry about it. You'll have more time. Please just give it back to me at the end of class. If you don't write anything down, that's also just fine. It's also totally fine. The last two topics that I've got that I want to talk about today, like I said, are a little bit grab baggy. They're kind of stuff that got left behind from last week that I want to formalize. I have told you about these things, I've demonstrated them to you, but I want to formalize these ideas. The first of those two topics is input and output streams. The command line programs that we have now written and that we have used have two different places that they can put data, at least two different places. They technically have up to 3 by default, but we're just going to talk about 2 of them. And we think about these things as streams of data. Do we all know who that guy is? It's not Bear Grylls, no. It's not me, no. This is an extremely satisfying YouTube channel to watch. But if you are going to watch it, I strongly recommend that you put subtitles on because he actually describes what's going on in the subtitles. I watched this for a long time, just kind of zen, like, this is awesome, watching this dude just making stuff out of nothing. And then I found out that if you put subtitles on, he's actually describing what he's doing, and it's not just him making stuff, but him actually describing it. And he lives somewhere in Australia, and he's gone through the process of like starting basically from nothing in this forest to smelting iron. It's very cool. It's very cool. It's worth your time when you have the time to do it. It's worth your time. So this is a stream. There are 2 streams of data that programs have, at least. There's standard input and standard output. Standard input is very generally where data comes from. So far with the code that we've written, it's the keyboard. We are reading from this thing called stdin. We do fgetS on stdin. When we call getchar, it's using stdin. Typically, this is the keyboard, but it can be other stuff. It can be files. It can be other programs' output. So another program we'll call printf. It will produce output. We can send data to be the input for our program from that one, or other devices that might be attached to the system. So data can come from, for example, this web camera right here can be an input source. This can be an input source for a program that we're writing. In Java, this is as simple as making an instance of scanner and passing it this specific object, system.in. In C, in the programs that we've written so far with fgetS, we have this stdin variable that's just available for us to use. stdin and system.in are the same general thing. Standard output is where data is going to. Typically, this is the screen, our terminal. We put stuff into our program, and when we call printf, it's writing out to the terminal or to the screen that we're working with. This can also be files. This can be the input of other programs. So input can come from the output of other programs. Output can be the input to other programs. It can be things like a printer. If you were here 20 years ago, if you were here 20 years ago and you were on Aviary, you could use a command on the command line to just print to the printer, to print to printers. And there were these old dot matrix printers that would just like spit out these reams of paper. Have you ever seen the paper where it's got those holes on the side and you just rip it off? There's printers that are just like bzz, 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 like this, and that's the kind of machine that they're going into. Output can also be 2 other devices. So We can change the source or destination of IO on the command line using these redirection operators. We have seen the redirection operator for input. Redirecting input to a program is using this less than symbol. What this says is when a thing that I've written, so let's say that I have a program here that's called myprogram.c. When it reads stdin, when we have fgetS with stdin, this is saying the contents of file.txt are going to be what gets read from stdin. So that file becomes standard input. This gives us the ability to effectively read from a file. We are reading the contents of a file in our program by reading stdin, by reading standard input. You can reverse that. Was that me again? You can reverse that and say, I want to write output to a file. This is a program that I've written called myprintingprogram.c. It has printf function calls in it. Normally that goes to my terminal, but if I use this greater than symbol, everything that gets written to the terminal will instead be put into a file that's called output.txt. We can effectively write to a file just by calling printf without doing anything special in our program that has anything to do with files. We can also communicate directly between programs without writing files or without reading files. This line here says, I have a C program that's called myprintingprogram.c that calls printf. I have a program here that's called myprogram.c that reads from stdin with fgetS. The data that my printing program prints to printf will be read by what my program is. It's going to be read by my program. So printf is effectively going directly to the fgetS in another program. This one single operation does not create a file. It doesn't create any files. These two programs are just connected to each other. They're directly connected to each other. stdout becomes stdin for the other program. The other subtle difference between these is that you can accomplish what this is doing by doing this, this, and then this. So write all the output to one file and then redirect standard input to be another file, like this. The difference between that and this is that these two programs are running at the same time. They are happening concurrently. Concurrency is something that you'll see in operating systems. Concurrency is something you'll see in operating systems. And that whole idea of fgetS blocks becomes important because you have two programs that are running at the same time trying to talk to each other. For us, what we need to know about this is that when I put that pipe in between, printf from here goes to fgetS from here with no extra files. It's just a direct connection between these two programs. Printf from here goes directly to fgetS here. That's ultimately all this is doing. Any questions about that? Great. Yeah.
The other day I was trying to type the output from multiple different programs into one program. How would you do that?
That's a good question. Each program has only one standard output. Each program has only one standard input. You would need to have a more complex setup than this. And I am going to suggest that you take operating systems to answer that question. It's conceivable to do it, to basically take multiple standard outputs and then concatenate them together into one single thing. But that requires working with lower level primitives than we're able to work with right now. Okay. So we could just stitch a bunch more. So if my printing program prints with printf, if my program gets input with fgetS, but also does printf, I can put another pipe here and another program that reads with fgetS. And it can be as long as you want, as long as it makes sense for what you're doing. Normally, it's going to be like this with just one, but it's conceivable for it to be many, many programs long. Yeah.
So in assignment 0, we had to experiment a little bit. With
Yeah. Yeah.
My question is, when we're writing to writing an alpha onto a text file, how do you not overwrite the text file? Because that's pretty much what ended up happening in context.
Two greater than signs, yes, will append to the file instead of one. So one greater than sign basically deletes it and then makes a new file. Two greater than signs will add to the end of it. We're good with this? Good. Let's start this. No, I'm not going to start it. I want to quickly talk about next week. So next week is the weird week. Next week's that weird week. It is the long weekend this weekend. So on Monday, the university is closed. On Tuesday, what's going to happen is we'll have a normal class like this. On Wednesday, class is canceled because I'm going to the farm. I'm still kind of mentally trying to decide if I should just make a video for you to watch independently on your own time. But I haven't committed mentally to that yet, but that might happen. And if it does happen, I will tell you for sure on Tuesday to like watch for it, basically. On Thursday, we will have a regular class. And then on Friday is our term test. The material that's on the term test, whatever the material is that's on the term test, will end on Wednesday of next week. So whatever we do on Thursday isn't going to be on the term test. I hope that doesn't mean that nobody comes to class on Thursday, but the material that we do on Thursday, I'm not going to be like, haha, you got to do all this stuff that we're talking about on Thursday on the term test the next day. Yeah.
What would be kind of like the scope of the term? Linux or like the shell scripting stuff, or like C or programming?
I'm not going to be asking you questions about the command line programs and how to make directories and stuff. That is a learning outcome from this course, but I don't care. You can figure that stuff out on your own. I'm a lot more interested in the C programming things that we've done and the programming practices things that we've done. I will talk more about the test next week, and I'll formally make time for it in a lecture. When we go from 1,000 level course tests to 2,000 level course tests, there's a change that happens where in the 1,000 level course tests, you're focusing primarily on programming. Most of the questions that you're answering in 1010, 1012, 1020 are program this little thing, program this little thing, program this little thing, and maybe have some concepts that are related to that. But what we're doing in 2,000 level tests is going to be a lot more yes, there is some programming, but we're now focusing a little bit more on you're actually writing responses to things. So written things are going to be in the scope of this test. If it's a question about the test, I'm going to ask you to hold it until later, okay? Yeah. Sample exams. I don't do that generally because if I gave you the test that I gave 5 years ago, it's not going to look anything like the test I give you this time. And if I give you a sample, I don't want you to... Have you heard of this idea of these large language models being overtrained towards some specific target? I don't want that to happen on a test. I don't want you to be like, this is exactly what my test is going to look like, and then show up and it doesn't look anything like that. I'm going to talk more about the test. I want to be respectful of your time right now. Class is technically over, but I will make time for us to talk about this. So let me skip ahead here quickly. The only thing that we really didn't cover here today is this part. You should be able to write safe code in a programming language that makes it difficult to write safe code. You should be able to describe concepts of in-application memory management, specifically the runtime stack. You should be able to explain how and why functions like scanf are not safe, by doing things like describing the runtime stack, how that code changes the runtime stack and what's going on there. You should be able to explain the concepts of standard input and standard output and give examples of each. You should be able to choose which one of these operators you're going to use given a context. That's it for today. Thank you all for coming out, and I will see you all tomorrow. Bye, everyone.